So our next speaker in the session is an old friend and colleague, Christina Silberhorn from Paderborn University. So good morning, Christina. I mean, you almost don't need an introduction. We know you as a community, but I thought I should at least give you your title so that the audience knows. And today, Christina is going to talk to us about nonlinear integrated quantum optics and pulse light and photonic networks, unless it's been error corrected to something newer.
No, thank you very much, Bill, for the introduction. Good morning also from my side. And thank you for the organizers to giving me the opportunity to present our work today. Now, what you see on this page is one of the devices I will be talking about later on. So before I really start to go into the topic, what I wanted to talk to you about, I would like to introduce briefly my group. Basically, we are the Integrated Quantum Optics group at Paderborn University. And since we're having different areas which we're researching, we have subgroups. And I will explain you later why I go into detail there. On the one hand, we really do technology, and I think this is really important that we really can do the underlying technology ourselves, mainly lithium niobate, but we also use KTP and nowadays also LNOI, and the group leader there is Christoph Eigner. Now, if you go from technology in the clean rooms, the next step is you really build devices. And for these devices, the group leader in my group is Harald Hermann. We do their, device fabrication with modulators, and you will see one of these devices. And last but not least, we do what we call quantum networks. And this is basically where many of you probably know me from, where we really do the quantum applications. And the reason why I present it like that, I think we have now, we are in the situation that we really need the technology, and we have to develop this technology. And it's great to have all these things in-house. So with that intro to the group, let me try to tell you what I wanted to be talking about. So I'm a photonics person, and I want to talk about photonic networks, but I want to show you different ways how we can realize that networks and to demonstrate you different components. On the one hand, this is now almost established as integrated optics, which is a great tool. Then I want to talk about time-multiplexed quantum systems, and then last but not least about temporal modes of pulsed light. And in fact, these temporal modes of pulsed light, hopefully you will see why I also call them a networks, or in other words, a high-dimensional hyperspace. Now let me start with integrated quantum optics. And more specifically, what we do concentrate here in Paderborn is about nonlinear integrated optics. Now, this is kind of the vision we have. We want to explore the lithium niobate platform. Why that? This is a quite well-established platform. And one thing we have really a minimized decoherence because we can really produce very low loss wavelengths. Now, with all integrated optic systems, we have a stability and scalability of these systems. So this is great because it's integrated devices. Now, if you go to a platform which has a Chi2 nonlinearity, which we do here, the big advantage is that we have very efficient photon pair generation via parametric down conversion, and maybe equally important, we can have fast electro-optic routing. And this is how we envision devices might look, practical devices for real-world deployment. We can have photon pair generation, we can have polarization control because our waveguides guide both polarizations. We can have single photon conversion to different wavelengths, phase shifters, and control all electro-optically. One thing I'd like to mention, you can also include detectors on this platform. Now, because I don't have much time, I just want to brush or show you a few flashlights. So devices which we have implemented were in the last years plug-and-play single photon sources. This is heralded single photon source with good performance, noon state photon sources, the generation of polarization entanglement with degenerate frequencies, and free photon states via cascaded PDC. Now, the device I want to show you a little bit more is homomandal interference on chip. Well, homomandal interference I don't have to introduce to that audience, but it's two-photon interference at a 50-50 beam splitter where we only find the two photons exiting at one port. Why is it interesting? Well, it's the basis of measurement-induced nonlinearities, and it's a very fundamental thing for all kinds of different applications. The way we test that is that we put two single photons on a 50-50 beam splitter and introduce a delay and look for the dip, so the very famous homomandal dip. Now, how do you do that on a monolithic device? Well, you include a parametric down conversion source, a two-photon interferometer, and a value delay line. And this is how we did it. So here you find the device. We pump a PDC, we generate 2 photons, horizontal and vertical polarization. We switch the polarization. We have a polarizing beam splitter which separates the 2 photons. And then we have here another segmented polarizing beam splitter. And here at the end, a tunable 50-50 beam splitter. Now, what is that segmented element here? And it's kind of key here. Well, because our material is birefringent, the different polarizations travel at different speed. And depending where we kind of switch the photon, we can introduce the time delay. If you do everything correctly, this is the theory, this is the experiment, and we're quite happy that we are now at the stage where we can demonstrate that such a complex device with electro-optic control can actually operate and work. We find visibilities over 93%, and the time delays we can introduce are 12 picoseconds. I think this is a great achievement. I believe that it's a great achievement because that means we can do synchronization events. With that, let me switch to the next topic, which is time multiplexed quantum systems. Well, here you see we go from the integrated system again to a more traditional system, and here is a typical setup of that, where we still use bulk optics. This is because we also want to explore which other kind of systems can be built up to really scale up photonic systems. And one thing where you want to look into these scaled up photonic systems are discrete quantum walks. And by now I think they are also quite established, but let me introduce briefly what they are. It's kind of the quantum version of a golden board. So we have a ball which is falling down this board, and you're monitoring at the end the statistics. Now, if you make that quantum, instead of having a ball which can go these different lines, we allow for superpositions. And mathematically, that means that we're creating a Hilbert space which consists on the one hand on the position, on the other hand we have this coin which decides where we go to the left and the right. So this is a coin state, this is a step state. And if you do that and you have a coin-dependent displacement on this position space, you kind of implement exactly this system. And you can differentiate between quantum and classical. Classically, we expect the famous binomial distribution. Well, quantum mechanically, well, you get interferences, massive interferences, and here you see it over 100 steps. And depending on the initial state and the initial coin, you can get different distributions. And this is for Hadamard coin, where you can see that you can get widespread coins. Now, we have started to do these experiments more than 10 years ago. And the question is, how do we implement such massive interferometers to really scale them up? And I would like to emphasize that even with integrated optics, if you really want to have 100 steps and more, that this is still a challenge. Now here, this is the reason why we did it in the time domain. Our coin is implemented by half-wave plate, so we really have the two-dimensional Hilbert space. And then we introduce a polarization-dependent delay such that we implement the delay in time. And if you repeat that, so we do that in a loop geometry, what you can then get is really this quantum box. And here on the right, you see really theory experiments. So this is really experimental data, and it's already 10 years old. But the reason why I brought them to you is that you can see in this system, you can get extremely nice system in the sense that you have a very good resource efficiency in general, because you can scale it up to 28 modes here. And you have on top of that, the ideal homogeneity. So the quality of the data is really good and is very much to the theory. Now, the other advantage is that this half-wave plate can be rather easily changed to an electro-optical modulator. That means that you can dynamically control these different couplings, and you can implement all kinds of simulations. And I don't want to go into details in there, and I would like to refer to the publication we had. But the last years, we did different simulations of the circuitries to study, for example, topological effects, topological invariance. We slightly modified these systems. We did quantum walks with 4D coins. We also did 2D quantum walks. And we started measurement-induced dynamics in the systems. Now, I want to present to you our latest work on that. And this is again the circuitry, but now we finally included also PDC states into photon states. Why did it take so long? Well, there was other things to do, but on top of that, you need a very specific engineered source. So we have a source of pure single photons with a picosecond domain. What can you do with that? Well, the first thing we did, we used our circuitry to synthesize very specific time-bin single photon superposition states. And here is kind of just a glimpse or to tell you what you do. So we produce these states. And then we implemented a circuitry which allowed us to create different single photon time bin superposition states. On the one hand, with twice the same single photon state, and you see them here. The time bins they have look exactly the same. And the second case, we implemented the same thing in intensity, but we introduced a phase shift of pi in between. Why did we do that? Well, we studied the Hong or Mantel interference again. And this is because we wanted to understand in a rather complex network, we have different interferences. What is the difference between local and global interference? And let me show you what I mean by that here. So what is local interference? You see that we have these different time bins, and these two different time bins of the blue and the red state can interfere each individual part, the left part on the left beam splitter and the right part on the right beam splitter. And this is the same as the case for both cases where we have a shift of pi in between these superpositions or not. What do we expect? Well, a standard home dip for these individual things means that you get your home dip. Nothing surprised, and there's no difference between those two. Now, in a home dip, we can also look for a global interference property. What do I mean by that? I mean by that basically I look for that jointly together, and here you see that we looked for the two blue detectors. We didn't distinguish which of them detected a photon, and the same was true here for the red detectors. Now, what's interesting that you get kind of a time-resolved Hong-Mantel dip in the sense. And what that means, while on the left-hand side, they still completely overlap. On the right-hand side, these two states are completely orthogonal to each other in the way which we will later see also for the time multiplexing. What does that mean? Well, if these two states are orthogonal and we look them as a whole in that, there's no interference there. And that's exactly what happens. So although locally we do see the complete interference, globally the interference has vanished. And this is a great engineering tool which we now can use and look from these networks from a different perspective. What we basically do, we can see just there's a photonic state and we look for the superposition inside these photonic states. And if you do that, you basically can now have a new tool. And I like this new way of looking at networks from the photons perspective. Since I don't have too much time left, I would like to switch now to the last topic, which is temporal modes of pulsed light. Now, what are these temporal modes? Well, temporal modes live in the time frequency phase space. And time bins I just have been talking about, and I would like to mention there's plenty of work on these time bins and superposition of time bins, where you do encoding of the different states in time. Nowadays, people also have started more and more to use frequency bins. Well, there you use your encoding in frequency. Every individual frequency is one different coding of the alphabet. Now, one thing which we have been looking now for several years, is to look on a completely different, well, a somehow different way of encoding information. And we use that and introduce these temporal modes. And one thing you can directly see, these temporal modes are neither frequency nor time bins, but they kind of in between because they live in a space which is occupying time and frequency in equal basis. Now, to be a little bit more specific, you can have monochromatic frequency bins, and this is what you do in a standard textbook approach for quantum optics. Now, what you can do, you can define superpositions of these different frequency bins. And actually, you're used to that in the spatial domain if you form Gaussian beams. But if you do so, we can now create different bases which are superposition of these different frequencies. And here you see that we used the Hamid Gaussian function as these bases, and all these functions are orthogonal and span an orthogonal Hilbert space, a high-dimensional Hilbert space. Well, we have one problem with that Hilbert space. It's very convenient because this is what PTC basically gives you naturally, and you can also send them over fibers quite nicely. But these temporal modes overlap in time and frequency. Overlap in the sense not in an integral form, but if you look individually for time and frequency, you will see that all these modes occupy some of these places. Now, one thing which we introduced was the quantum pulse gate, again, already 10 years ago. What is that device? It's basically a device where here you see our input state, and depending on a pump which we can choose as a knob, we can address only one of these input states. And here you see that we addressed only the first and mid mode. This gets converted to different frequencies while the rest is going through. You can do that with a different, like the first quotient, or you can do that with superpositions. How does that work? Well, the realization or the way it works is a group velocity matched some frequency generation. The pump and input frequencies have the same speed of light. You have some frequency generation process, and this is kind of the transfer function, but this is how it basically works. What you need for that is very specific materials. In our case, it's a home-built lithium niobate waveguide with 4.5 micrometer Poling and a type 2, where the input is at 1550 and the pump has to be at 860 nanometer. Now, what is that good for? Well, what it is good for is that you can select arbitrary temporal modes in time or frequency superpositions, in particularly also these temporal modes, which I just showed you, the Hamilton modes. And we believe that this opens up a new way of encoding. And to demonstrate that, one thing we did first was that we reconstructed POVM's element of 8 7-dimensional mutually unbiased bases. So basically what we demonstrated in this paper is that you can have a 7-dimensional Hilbert space. Now you can, for example, do quantum cryptography with that, where you're not restricted anymore to that 2 dimensions like you typically are, but you have these 7 dimensions. And I think what's really also quite nice is that we can look in all different kind of mutually unbiased bases here. So we really can not only have 2 bases, but we can basically choose our bases at our will. Why is that interesting? Well, we have implemented several different applications, and again, because of time constraints, I don't want to show you too many applications in the direction of metrology or communication, but if you're interested in that, I'm happy to talk more about that. In this talk, I want to concentrate on a different application, which is basically coming back to the second part of my talk. We introduce here the concept of a measurement-based quantum walk. What do I mean by that? Well, you can look at a quantum walk in a more abstract way. So basically what we measure in the quantum walk are probability distributions at the end, and quite naturally, the way you can write it, it's kind of the overlap, or you just calculate these overlaps. Now, if we ask what is the psi final at the end of our quantum walk, well, what it is we have an input state and we operate with that input state with a unitary operation, and then we measure x, where the x is that position. Now, what that means is our unitary operator operates on the input state. Now, if you look at that formula, you can equivalently also say, why do we have to operate on the input state? We can equivalently also just operate on the output state. Well, what does that output state mean? Well, that means nothing else that we just change our measurement. And to illustrate what I mean by that, I would like to show you in terms of polarization. So typically, if you kind of have an operation of a half-wave plate in H and V, the half-wave plate rotates the polarization, and the polarizer, then you analyze it. Equivalently, you can also change your polarizer and just rotate the polarizer, and then you have to implement the same operation. And this is exactly what we did in terms of quantum walks. And instead of using different positions, we use the frequency bins and we use our quantum pulse kit, which I just showed to you. Why is that interesting? It's interesting because if you want to implement even larger quantum walks, what we want to do, we really want to implement a lot of steps. And here you see the scaling. So we need a lot of different modes. I showed you already for the time multiplexing, we implemented 28 steps and 406 beam splitters for different points. Now, if you want to go to even more complex system, we can directly use the measurement approach, and this is a new data. Basically here, in this way, you're not restricted. You can dial up every step you want. And for example, here we had 400 steps, which would correspond to 80,200 beam splitters. I think it's very hard to do that in any optical experiment if you want to directly do it in a quantum walk experiment. It is the bins, we have 46 bins, and we really believe that this quantum pulse kit can be a powerful tool to operate on that. Moreover, we can implement arbitrary coins, and we do the quantum walk in a 4D hypercube. This Fortunately, it doesn't work now. Anyhow, but we could measure these different probability distributions, and the similarity of our walks is excellent. So basically, we see with that, we can implement in the frequency domain arbitrary coin states, all kinds of unitaries on a really large Hilbert space. And we're quite excited to work, well, to continue this research and actually to try to see what we can get out of that. With that, let me summarize. And I know that it was a rush through different topics, but I was asked to do that in 20 minutes. So I actually just wanted to give you a glimpse on these different topics. I started to show you a little bit of our non-integrated optics activities, where basically the main thing is that we now also can include nonlinearities and, more importantly, electro-optical modulators. I think this is very important because we have to have fast electro-optic routing. And in particular, if you're talking about quantum communication, or we combine quantum communication with some processing, it's quite frequently not said, but fast routing, fast control is also an important ingredient. And the second part, I showed you our progress for time-multiplexed quantum walk systems, but basically I want to advocate a different way of looking into that. These networks, instead of saying we have these individual modes and we look in all these modes locally, we can also take a different view. We can ask, well, let's look at this network as a global system and ask which kind of superposition of single photons do we generate. And then we have a new handle to actually tailor and customize or engineer our systems. Finally, I showed you our progress in the temporal modes business, where basically I showed you that we can handle all kinds of different modes with quantum pulse gates. And I showed you the first applications, or one of the first applications in the area of processing, where we basically did a very large quantum walk. With that, I would like to thank you for your attention. I would like to mention that this is, of course, not the work I did on my own, but there are many people behind the scenes, and I actually want to really also thank my group who actually did all this work. Thank you very much for your attention.
Christina, impressive talk like always. The results are just getting more and more amazing as time goes on. So we have a number of questions, but normally we take questions from the audience, but I'm going to take questions from the invited speakers first. So the first question is, what is the average loss of your PPL and waveguide? And is there any way to reduce the loss to the theoretical limit?
Okay, so I haven't been talking about that. So you're talking about the nonlinear waveguides. We are using a very established technology here, and we can go down to 0.02 dB per centimeter. So this is extremely low. If you ask me what is the theoretical limit, I can tell you the theoretical limit would probably be the limit of bulk, which we don't reach. But it's really, the waveguide loss is not the issue. If you ask what is the issue at the moment, it's really the interfacing. And I haven't been talking about that either, but we need codings for that. And then we have to have mode adaptation if you want to bring them to detectors. And this is what we're working on. And this is probably also one of the reasons why integrating detectors would be great. But there's still quite a lot of potential in that.
Okay, so following that question up, what is the performance of your chip-based PPLN entangled photon source? So what's the brightness, the fidelity, etc.?
Oh, sorry, I don't have the brightness. I don't have the numbers right me, but look it up. This entanglement source is published in Nature Partner Journal information. It's basically the reason why I don't know the brightness directly is that we always limit the power. So we don't have any problems for these brightness in terms of we can pump them in harbor. We have extremely high brightness, but we have to reduce the power in order not to generate too many multi-photon components. So thus the brightness is not the main thing. In terms of fidelity, I think we are 98 or something. The fidelity is extremely good. That's not a problem.
Okay, so as a theorist, I want to ask theorists have to ask experimentalists questions. So, I mean, I'm really intrigued by your new quantum pulse or your pump gate, the last gate that you kind kind of thing. It's not the kind of gate we normally think about in quantum computation and various things like this. So, I mean, it's an unusual gate. So where does it fit into the broader thing? It seems to give me some new abilities.
Okay, maybe gate. It's more gate. It's not a circuitry gate, definitely not. But it's a gating. So you basically can really gate pulses depending on the shape. It's basically you can implement all kinds of linear optics with that, but you're not limited in which optics you're implementing. And this is why we demonstrate this measurement-based quantum walk, because at the end this is just a unitary, a linear unitary for all these. And this shows this gate quite nicely. So you can basically implement all kinds of different unitaries. Is that answer enough for you?
Yes. Sorry, I'm just, you see me large, but I'm just trying to read a question. A question from the audience. What do you find between the global and local multiplex system's unique properties? So the question is, you have global, you have local. So what's the kind of trade-off between the two?
Well, you can engineer it. The way I see it is the global property basically is given by the coherence properties of your system. Now, the coherence property of the system is perfect, right? And you can control with the coherence properties, so the G1 interference, the G2 interference. And this is a fascinating thing. So basically, people like to tend to think, oh, these are these individual channels, and I look at that. But this is not really true. You have a single photon which is spread across the whole channel. And if you go from this viewpoint, you can interpret your interference completely different. And this is what's very nicely balanced in this local versus global interference. And well, I personally think that looking from how many photons are there and in which superpositions are gives you a completely different way of understanding the system, and actually also the complexity. It's not very complex. Well, many modes is difficult, but this is what you can do. Many photons and many modes, this is a different question. This is what we want to highlight there.
Yep. So thank you very much. I mean, given that time is on, I really always enjoy your talks. I look forward to seeing the amazing progress that you're going to have in a few months or in 6 months' time. So thank you for coming in your morning. And please, there may be some questions in the Q&A. Please answer them as you can. So thank you, Christina.
Thank you very much, Bill. See you somewhere soon, possibly.
Yeah,
Bye.
exactly.